Good afternoon, everybody.
Afternoon, sir.
Okay,
Afternoon, sir.
all
How are
right,
you?
good. Uh, well, I won't complain. Let's just give persons who are joining another minute or so now. Hate to keep you waiting, but I guess we just have to. I want as many persons as possible. So another minute or so, please.
Afternoon, everyone.
Good afternoon, Mr. Bro.
Yes, sir. How are you doing?
Not too bad. Not too bad.
Oh, okay, great. Sir, quick question. Um, my timetable had the tutorial for 5 and 6 on a Wednesday. You don't have the 6 o'clock class.
Um, well, usually, but a
Oh,
change has taken place since last week.
okay, okay,
Um, yeah, it's some. Remind me if you don't hear me say anything about it when more
okay,
people are here. Just remind me. Later in the
okay,
class.
sir.
But yeah,
Okay,
there has been a change in the timetable.
okay. Because I joined that tutorial last week. However, I found that there was another meeting for that week. So
Yeah, some right. Some changes has taken place.
okay, sir. All right. So 5 o'clock tomorrow then.
That one is out also.
Seriously? Wow.
Right.
Okay,
Yeah.
okay.
So
All right.
some changes that may
So
have some
your
impact.
consultation always remain the same though.
Yeah, yeah.
Okay.
I mean,
All right.
practically anytime you want to communicate with me, you can just send me an email.
Right.
And once I will communicate. So you don't really have to wait for the consultation hours if
Okay.
you have a pressing issue.
Okay, sir. Noted. Thank you.
All right. All right. I think we can start now. It's almost 10 after. And as I was saying earlier, there are some changes that I need to advise you about. But let's do it when there are more persons here. I expect maybe around 20 more persons at least. All right, so today and next week we will go through electromagnetism and magnetic circuits. Uh, in the past, persons usually fret when they hear electromagnetism, but it is not the one that has to do with a whole heap of fields, the very difficult fields that persons usually have challenges with from year to year. This one is going to be very simple, something that you would have done from fourth form. So everybody should enjoy this topic and be able to solve all of the problems them quite easily. All right. So when you think of, you can turn on your mic for a half a second or so. When you think of electromagnetism, what do you think of really?
Sir, current and fields.
Current and fields. Okay.
Yes, sir.
I said hi too.
magnetism and the
Flow of
electricity.
electrons in magnetic fields.
Magnetism. All right. So
Or
current and fields, um, magnetism and electricity.
Electricity, magnetism caused by electricity.
All right. Good. All right. Good. Right. So everybody basically has an idea. So as I say, it should be smooth sailing this evening. All right. So persons are joining minute by minute. All right. So electromagnetism speak to the fact that you can get magnetic lines of flux from current. So current flowing in a circuit will have associated with it magnetic fields. And the diagram on the right shows you a, a piece of conductor bent. So you can see the current traveling in two different directions, and then you can see the magnetic fields around the conductors. And you can notice that they are going in different direction, and the direction is associated. The direction of the fields is associated with the direction of the current. Right? Now the fields, the magnetic fields that are produced have similar properties to that of those produced by a permanent magnet. And you may recall some of those properties of a permanent magnet. All right, but not to tax your brain too much yet, we'll just do a quick review. So the magnetic lines of flux produced by a permanent magnet has the following properties. No. The flux flows from out of the north pole of the permanent magnet into the south pole. So it flows through the surrounding space and from north to south, but inside the magnet itself, it flows from south to north. Right? And these lines of flux, each of them form a closed loop. And you know how these, although you can't see magnetic lines of flux, are totally imaginary, their effects are real, and you can plot the path of each loop by using iron filings, maybe spread over a piece of paper and have a magnet under it. If you do that and shake the paper, then you will see the filings line up in these kind of orientation. All right. So the magnetic lines of flux form closed loop. They don't intersect. So although you have so many of them, and remember all the space. So even though you don't see anything drawn right here or here, all of the space is filled up with the flux, right? All right, so there are a couple properties that you probably won't see normally in the book, but I've written them this way in order to explain a couple of the properties. All right, so properties 4 and 5 has to do with when two permanent magnets are close to each other, and it also relates to electromagnets. All right, so if you want to see the properties though listed, you can find them in the Hughes textbook at this page in the ebook. All right, so I will explain these in a little bit more detail. What I'm saying here is that if the lines of flux are parallel and they're traveling in opposite direction, they kind of have a kind of canceling effect. consider one direction plus and one direction minus. And remember these now are like vectors. So the vector sum would be less if you have a subtraction taking place. So that is what's happening here. But if they are traveling in the same direction, then the vector sum is increased, right? So it results in a strengthening of the magnetic field. All right, but this will be made clearer immediately. So let's say we have two permanent magnets and we have them positioned like this. So the one on the left, the north pole is at the top. The one on the right, the south pole is at the top. What do you expect to happen here? Oh. Anybody? Without reading.
Happen where, sir?
In this situation where you have these two magnets here.
Like charges repel and opposite charges attract.
All right. So so tell me your final conclusion then.
The magnets will attract each other, so they will stick together.
All right. Okay, good.
Current in the magnetic field flow from north to south.
Currents?
South to north.
Currents?
The lines of the magnetic the lines of the magnetic field flow from north to south or south to north, but not north to north and not south to south.
Okay. All right. So we have two poles with their poles positioned opposite to each other. Right? Now the space between these two I have two arrows representing the flux from either magnet. So the blue one is associated with this one on the left and the red one with the one on the right. Now, because the flux flows from north to south, where this flux now is moving from north to south, right? So it's pointing down this way. And this one, again, on the right, is moving from north to south, so the red arrow is pointing up. All right. Now, remember what we said, that if they are traveling, if the flux are traveling in opposite direction, you have a cancellation of the flux. So if the two magnets are of the same size, same dimensions, the flux in here are going to be totally cancelled, right? Because they are going in opposite direction. And when they are cancelled now, so there's nothing in here now that is preventing these two magnets from coming closer together. But on top of that, now you have, as 876G said, the flux now is going to move from the north pole of one through to the south pole of the other, through the air, and travel through that and come back around. Right? And as they do that now, these flux now are kind of behaving like, some elastic bands that are stretched, that are under tension. And they naturally want to release the tension. So they try to shorten themselves together. And as they shorten themselves together, they pull the magnets closer together. So in this situation where you have the opposite alignment of the poles, you have attraction of the magnets, right? And that is clear purely because there's no flux in between them, and the flux from one magnet pulls the other magnet to it. All right, so it's happening in both cases for both magnets. So the long and short of all of that is that opposite poles or unlike poles attract each other. All right. Here we have the opposite situation where we have the north poles of both magnets now adjacent to each other. And then you can see the flux orientation between them. Now, in this case, all the flux are traveling in the same direction. And because they're traveling in the same direction, them kind of strengthen the field inside here and basically keep these apart. In fact, they will push them apart. So when you have like poles aligned to each other together, you have a repulsion taking place. Right? So remember that the fifth rule was that if they are parallel and traveling in the same direction, you have the repulsion of the two magnets. All right. So that basically would cover the properties of a permanent magnet, and you'll find similar kind of situation with electromagnets. Now, everybody probably remember seeing representation of a current carrying conductor with dots and dots so on the right here and crosses on the left, right? And well, the legend down here tells you what they represent. So the cross represent current flowing away from you, flowing into towards the screen, into the screen, and the dot represent current coming out from the screen towards you. Right. These are also described as the tip of an arrow, the dot. So you would see an arrow. I mean, if an arrow is coming at you, you would probably only see a dot. But if you are the person who's firing the arrow, you would. There are some tail feathers at the back of the arrow that you would be seeing going away from you. All right, and the direction of the current help you to figure out the direction of the lines of flux. So these concentric circles with the arrows on them are the lines of flux around this current carrying conductor, around these current carrying conductors. All right, now how you know the direction of the lines of flux is that you imagine that you're holding the conductor with your right hand and your thumb is pointing, your big finger is pointing in the direction of the current. Then all your other fingers now will be pointing in the direction of the lines of flux. Right? So in the case on the left, your thumb would be pointing towards the computer screen and your fingers now would be moving in a clockwise direction. And the opposite is true for that on the right. So yeah, just practice holding your fingers in the direction of the current so that you kind of remind yourself where the direction of the flux is going. And believe me, we will use in these dots and crosses at occasions from now, because it's useful in helping to analyze how magnetism flows inside the machines. All right, so you will meet this again especially if you're doing well, you'll meet this again later on in this module, and also in drives too. All right. Any questions so far? All right, so let us talk about magnetic flux. So we have looked at the lines of flux. Now there's a relationship between those lines of flux and something called flux density. Now density basically speaks to the amount of the flux density speaks to the amount of flux that is in a particular area as a unit area, because usually referencing to 1 square meter. All right, but the area can be different. So it's the amount of flux in a particular area. So this is representing a lot of flux going through a particular area here. All right, flux is measured by the unit Weber. I understand it's the German pronounce the W as V. So if you were a German, you would say Weber. Flux density is given by the amount of flux divided by the area, and the unit for flux density is the Tesla. But you can also see that it could be Weber per meter square. All right. So A is this cross-sectional area through which the lines of flux are passing. All right, now a little question for you. At the right of your screen, at the top, you see it could be 2 magnets, or it could be a 1 magnet with a horseshoe. Well, let's say it's 2 magnets. So a north pole and a south pole are close enough to each other. All right, and the flux are traveling as usual from north to south. Below them, so below, where's my mouse? You have a conductor carrying current, and you can see the lines of flux around it also. Now the question is, what will happen if I take this conductor and place it here between these 2 poles?
Sir, it will get pushed downward.
Say that again.
It will get pushed downward.
To get pushed downwards. Oh,
Sir, the fields will curve around the object.
fields will curve around. All right, good. So
the field above it would be above the wire would be stronger, and below it would be weaker because it's in the same direction above, and then below it's in opposite direction, so you get weaker.
oh boy, this is very good. It's very good. I think we're going to have a very short evening this evening. All right. Yes. All of you are correct. So yes. So the figure on the left here now is representing the conductor now placed inside the magnetic field, right? And as somebody was saying, you can see now the direction of how the fluxes are moving. At the top here, they are in the same direction. On the bottom here, they are moving in the opposite direction. So when at the top where you have the moving in the same direction, you have a strengthening of the field. So you can see that, yeah. But you can also see the curving taking place. So it's like you're moving up. But down here at the below the conductor now, you can see the cancellation or the weakening of the field. So you don't see any field down here for a good portion of the diagram. So because that cancellation is taking place now, there's nothing preventing this conductor from moving down And then when these magnetic lines of flux now above it start to straighten back out themselves, because you know they are under attention now, so they're gonna try to, like the stretch elastic cord, they're gonna try to straighten back up themselves. When they straighten out, they push the conductor down, right? So you can, yes, somebody was right. Without even going through all of this process, he knew that the conductor was going to move down. All right. So we can actually have movement of a current carrying conductor, and it's caused by the combination of magnetic fields. All right. So that conductor will experience a force, right? And the force is given by this equation, where B is the flux density, I is the current in the conductor, and L is the length of the conductor in the magnetic field. All right. The force, the field, the magnetic field, and the current are all at right angles, are perpendicular to each other, right? But there's a way to predict the direction without doing this analysis. You can also use Fleming's left-hand rule to predict the direction of movement of the conductor when everybody is at right, when you know the three components, the force, the field, and the current, are all at right angles to each other. However, if the field and the conductors are the conductor in this case are not at right angles to each other, then the force is given by BIL sine theta, where theta now would be the angle between the field and the conductor. All right. Clear? So normally when you see the sine theta, the absence of the sine theta, right, when you see the absence of the sine theta, it is assuming that there's a 90-degree difference between, say, the field and the direction of the conductor. So you have sine 90 equal 1. All right. All right. Now a current carrying conductor situated in a magnetic field is basically the principle of operation of in an electric motor. And I show you a little diagram of it. So of a basic motor, right? So you will see current from a battery flowing through the coils here, and so they're moving in this direction. I don't know what this direction is. Away from me over here, and it's coming back this direction over here. So, and then remember now that the field, although they're not showing you the field now, the field would be across here. So you have currents going in two different directions in these conductors, and interaction with the magnetic field will cause motion. Now, if the conductors are situated on a shaft, so the shaft here now, they will rotate. So this basically is how you get action with the electric motor. Plug in your fan, and magnetic fields are created, and both to form poles, and also in the conductor. So fields are created around the conductors also, and then hence you have that interaction and you have the rotation. So notice one is going up and one is going, the force acting on this side is going up, the force acting on this side is going down. So hence you have the rotation. All right, so a current carrying conductor in a magnetic field is basically the principle of operation of an electric motor. All right. Now, what happens if you have a conductor with no current flowing in it and you move it inside a magnetic field? Now, Mr. Faraday, Michael Faraday, did a lot of experiments with this kind of thing. All right. So sometimes he moved the conductor in the magnetic field, and sometimes he moved the magnetic field to and from away from the to and fro from the conductor. And he found that if he was to connect this conductor to a load, he will actually get a current flowing, right? Which means that movement of the conductor perpendicular to the magnetic field or in the magnetic field induces an EMF across the conductor. So movement of the conductor across a magnetic field induces an EMF in the conductor. Now, the direction of the induced EMF can be found from either Fleming's right-hand rule or from Lenz's law. All right, so these are something that you will need to read upon. They are in the textbooks. All right, so make sure you read up and understand them. So Fleming right-hand rule, again, you're twisting up your fingers at right angles. Your thumb, your index finger, and your middle finger. And you try to orient them according to the circuit, according to the diagram, to find out the direction of the induced EMF. All right, but the induced EMF can be calculated from this formula. E is equal to BLV, where again B is the flux density, L is the length of the conductor in the magnetic field, and V is the speed at which the conductor is moved in the magnetic field. All right, again, everybody is at right angles to each other. So the field is at right angles to the conductor and its movement and its induced EMF. All right. All right. So generally, the induced EMF is given though by E is equal to BLV sine theta, where again B is the flux density. L is the length of the conductor in meters. V is the speed in meters per second at which the conductor is being moved in the magnetic field. And theta is the angle between the field and the conductor. So notice now that you see that this conductor here in this machine is no longer at right angles to the direction of the lines of flux. So the sine theta will come in there. Right. Now, note, since you have an induced EMF here, if you attach a load, in this case a bulb, to the terminals of the conductor, you get current flowing through the load. Right. Once there's a closed circuit, that EMF will drive a current through the load. All right. This essentially is the principle of operation of a generator, right? So a conductor is moved at very high speed with inside of a magnetic field. An induced EMF develops across the conductor, and that induced EMF, if it is connected to a load, will cause current to flow in the load. All right. All right. We won't be too interested in what's happening here right now. All right. Well, we basically want to show that moving the conductor in a magnetic field is the principle of operation of a generator. So you're actually seeing electromagnetism at work. All right. So we're showing you applying it to see how it applies in the motor. We have now seen how it applies in the generator. And we're going to look at the transformer briefly also. All right, so you would probably recognize this as a transformer. Has two coils, and the coils are called primary and secondary. The primary one would be connected to the source voltage. So we have an alternating voltage here connected to this primary coil. A load is connected across the terminals of the secondary coil. Now, when this alternating voltage is applied to the coil, a current, an alternating current, will actually flow in the coil. Right? Now, that alternating current will also produce an alternating flux. So as the current changes in magnitude and direction, the flux also changes immediately, concurrently with it. All right. Now that change in flux is changing across this coil, and it is changing across the secondary coil. And as it changes across, increases and decreases in magnitude, it induces an EMF across both coils. Right? So that change in flux causes an induced EMF to be developed across both coils. And if we connect a load across the secondary coil, we will get a current I2 flowing through it. So what is happening now is that the conductor is stationary. The conductors are stationary. But you have a change in flux that is moving across, and that movement of the flux across the conductor induces EMF across both conductors. All right, any questions? By the way, this could happen for a DC circuit, but it will happen for a very, very short instant. It will happen for the instant when you close the switch and current flows, and again at the instant when you open the switch and current stop flowing. So the flowing of current and the stopping of the flow of current will cause that induced EMF to be seen quickly. So if you have, say, a galvanometer connected across here, you would see the change in current flow at the instant when the switches are open. But that would be a tedious thing to be always switching. So alternating current is really the principle of operation, are the basic operation of the transformer. All right. So we have a situation where, let me let in, where you have a change in flux moving across the coils. Now the flux is said to link with the coil. Every time the flux passes a coil or a conductor, it links. It is called a flux linkage. Every time the flux moves across the conductors or the coil is called a flux linkage. All right. And as I said before, the coil could be moving also, and the flux constant. That you will see that when we do the AC generator. So the coil is moving and the flux. The flux, right? We move the flux, and the coil is stationary, right? Yeah, that also happens in the AC generator. Right. For very small AC generator, though, the opposite can happen, right? Where the flux is stationary and the conductors are moving. All right, but we're looking basically at the principle of operation of the transformer, right? Now, Faraday, as I said, did a lot of experiment with these. He states generally, and this is something again that you need to be able to state properly, that when there is flux linkage or flux cut in a conductor, an induced EMF develops across the conductors, right? So in a conductor that is cut by the flux, or in a flux that is cut by the conductor, you have induced EMF developing. And then he further goes on. So he has two laws. So he goes on to say that the magnitude of that induced EMF depends on the rate of change of the flux linkages. So rate of change of flux linkages. Flux linkages is equal to the number of turns of the conductor times the flux. All right. So Faraday's law can be written as we have here. E is equal to minus D. All right. So flux linkages. So remember the rate of change of flux linkages. All right, but this can be written as this because N is a constant, so we can take it out of the differential here. So as minus N d phi by dt, where d phi is the change in flux and dt is the change in time. So rate of change of flux linkages. So the change in flux are written as this, phi 2 minus phi 1, where phi 2 is the final value of the flux and phi 1 is the initial value of the flux. So bear this in mind. So the change in flux would be just like any change, a final value minus the initial value. All right. The negative sign has to do with the direction of the induced EMF, and Lenz's law speaks to this. All right. Anybody remember what Lenz's law says? Anybody?
The current induced in the coil is opposite in direction to the force that produces it. I think.
All right. Yeah. Right. And that current would actually be produced by that induced EMF. So that induced EMF is gonna try to set up a current that would. All right. So if we look at this diagram here, this induced EMF would tend to set up a current that would want to oppose the flow of I1. Right. So according to Lenz's law, so hence the negative sign of the induced EMF, because so it basically will be opposite to the sign of the supply voltage. All right. So in some of the textbooks you might not see the negative sign nowadays, but bear in mind that it is there, right? The negative sign is telling you the direction of that induced EMF. All right. So we have looked at the motor, we look at the generator, and now we have looked at the transformer. We can see that um, electromagnetic action is taking place in all of the machines, and the transformer essentially operates off the principle of electromagnetic induction. Right? Now, in the motors and the generators, you will also have induced EMF taking place, and this will be something that we will look at later on when we get down to Unit 5. All right. All right, so time for you to do some work. We have a coil of a moving coil loudspeaker. So this is the coil here. You can see the currents or dots and crosses there. Hopefully you can see it. I can barely see it. The coil of a moving coil loudspeaker has a mean diameter of 30 millimeter and is wound with 800 turns. It is situated in a radial magnetic field of 0.5 Tesla. Calculate the force on the coil in newtons when the current is 12 milliamps. All right, so I'm gonna give you 5 minutes. So by 6 o'clock, you should be able to tell me what the answer is. All right, so I'll give you 5 minutes to work this. Okay. What you want to find is the force. The force on the coil. All right. Any progress?
Yes, sir.
Okay, good. You have solved it?
So I got 0.452 newtons.
Okay, good. Good. Anybody else got it?
I got the same thing, sir.
All right. Okay, so this was a very easy exercise. Anybody didn't get it? Did not?
Didn't get it.
Say that again, Mr. Chambers.
I didn't get it, sir. Didn't get it.
Okay. All right. So what's the approach you use?
I was going to use a formula that says F equal B times IL, but I can't seem to find L.
Can't find what?
L.
L?
Yeah, length of the conduct.
Oh, okay. All right. Anybody know how to find the length of the conductor? Do we have information that can help us to find it?
Sir, you can use the diameter to find the circumference of one coil and then times it by 800.
Okay, because there are 800 turns. Okay. All right. Okay. You follow that, Mr. Chambers?
So you say I'm going to find the circumference and multiply it by 800.
Right. All right. So the coil is basically a circular kind of cross section. Right. They tell you that the field was radial too. So the field is coming out of these, right? So the coil now will be wrapped around here, around this kind of circular orientation. So if you find the circumference of one coil and multiply by the 800 turns, then you can find the length of the conductor in the magnetic field. All right. So this is it basically. The circumference is given by pi d. So and that works out to be that. And then the length of the conductor now is n the 800 times the circumference. That works out to be 75.398 meters. And then after that now is basically just putting in the numbers in the formula. F is equal to BIL. So yes, you get the 0.452 newtons. All right. Oh, all right. I have another one for you. So yeah, basically we're just looking at what we have done so far in electromagnetism, basically applying the two formulas that we have learned. Oh, I showed you. All right, try this one now. Try this one. A coil of 1500 turns give rise to a magnetic flux of 2.5 milliwebers when carrying a certain current. If this current is reversed in 0.2 seconds, what is the average value of the EMF induced in the coil? All right. All right, so you can go ahead, another 5 minutes. There's also a little hint. Hope you have seen it. Okay, how are we progressing?
Sir, we 37.5.
Say that again?
I was asking if it would be 37.5.
Yeah, it's 37.5. That's good. That's very good. Anybody else?
Yes, sir, got the same thing.
Okay.
So I'm just checking. Would it be negative 37.5?
No. Remember what we did earlier? All right. What about the ladies? How things going?
I finished with it.
No.
Listen, you're finished.
Go ahead and mute your mic.
Miss Montague?
Yes, sir.
How is it going?
Sir, it went somewhere, but not where everybody else went.
Oh, all right. Tell me your approach then.
Sir, I would honestly rather not.
You don't want to tell me your approach though.
No, sir, not today. Check me back next week, sir.
Oh, next week. Next week we're moving on, you know.
Yes, sir. I'll answer next week's question.
Oh, all right.
Sir, make sure to write that down, sir.
I don't know what the question is yet, but
yes, sir. I can write down Mr. Adams' name too.
Mr. Adams, she's putting you on the spot. She said that you haven't done it either. Yeah, no? All right. Anybody else? Anybody else got anywhere near 37? 37.5?
Sir, I know the answer is 37.5, but I don't, like, I know what the explanation is, but I don't understand the explanation, if that makes sense.
Oh.
So, would you mind just trying to verbally explain the answer?
All right. Yeah, man, no problem. In fact, we're just going to go to that next slide. Come on. All right, so the solution is here on the screen now. So we were given the number of turns, 1500, and the initial value of the flux was the 2.5 milliweber, and we know that they said that the current was reversed in 2 seconds. So we know that the change in time is sorry, not 2 seconds, but 0.2 seconds. So we know that the change in time is 0.2 seconds. All right. Now, since a reversal of the current will result in a reversal of the flux, so let me go back. All right. So what is happening? So that's why I gave you this now as a hint. So what is happening? Notice that the current is alternating, and as the current is increasing, the flux is also increasing, right? So any change in the current will cause a change in the flux. So when they say that the current has reversed, it has moved from one peak value, a positive peak value, down to a negative peak value. All right? So it has gone the same magnitude, but in the reverse direction. So up here it was in the positive direction. Down here it's in the negative direction. So it has gone. So it has reversed to its negative maximum, and it take 0.2 seconds to do that. All right. So initially the current was at. All right. So the flux was at 2.5 milliweber. Now, when the flux has reversed, it has gone down to minus 2.5 milliweber. All right. Everybody clear with that?
Yes, sir.
Mr. Johnson?
Yes, sir.
Yes, sir.
All right, good. All right, so that is what I was saying here. Now, a reversal, since a reversal of the current will result in a reversal of the flux will basically reverse to the negative value of its initial value. So therefore, the final value of the flux would be minus 2.5 times 10 to the minus 3 Weber. All right, so initial value was 2.5. The final value is going to be minus 2.5 milliweber. All right, then the formula is E is equal to minus n d phi by dt. So it's minus n, and we said that d phi can be written as phi 2 minus phi 1. The change in flux, and the change in time is 0.2 seconds. So after this now is just substituting the values. So minus has to do with the direction of the induced EMF according to Lenz's law. So minus 1500, and then we do the minus in the mathematics in here. So it's from phi 2 is minus 2.5, and for phi 1 it is 2.5, but you have a minus sign between them. So these two minus now combine to give you 5 milliweber. So 5 milliweber times the 1500, that's it will be minus 5 milliweber, sorry. Minus 5 milliweber times the minus 1500 divided by 0.2 give you the 37.5. Okay?
Yes, sir.
All right. Where's Montague?
Yes, sir.
Follow?
Yes, sir.
All right. All right. Okay, good. All right, so let us move on to magnetic circuits. All right, now this circular ring here is called a toroid, but it is a simple magnetic circuit. All right, so you will see a lot of this kind of thing, especially in the hues. Right. So it is a metal ring, kind of donut shape, and the magnetic material helps to concentrate the flux that is produced by this current. So you have a conductor wound around this metal ring, right? And each one of these is called a turn, right? So from here back to here would be a turn. So it has n turns of the conductor. This is a circle. So the circumference would be the length of this magnetic field, this magnetic circuit. Right? So the length here is actually the circumference. And then there's something called the mean circumference, because if you notice, you have an outer circle here, and an inner circle. So the mean circumference would be somewhere in the middle here. Similarly, you have a mean diameter, you have an inner diameter, and an outer diameter. So the mean diameter would be somewhere in here. So you will see questions talk about mean circumference or mean diameter. That's what they're talking about.
So, sir,
yes.
If we get a question, the length that we consider is the length of the circumference, and not the conductor.
Right. The conductor is wrapped tightly around it, so it is considered the length of the conductor too. Yeah.
Okay.
All right. Yeah, but it's the length of the toroid, the magnetic material. All right.
Sir.
Yes.
So not just any length, sir, but the mean length, sir, right?
Right. So yes, the length, yeah, Conrad, the length is the length of the magnetic circuit. Sorry. So that the flux will trace a path. So it's the path that the flux is actually tracing. Right?
Okay.
The conductor has to do with the number of turns of the conductor. All right. So it's the length of the magnetic circuit, or the path. So the magnetic circuit would see the flux flowing in it. So the flux basically form a closed circuit. So a magnetic circuit would have the flux in a closed circuit, or a closed path. All right. Now the material is usually some kind of metal, and metals are good at concentrating the flux, right? So more flux will flow through the metal than will flow through the air around it, because the metal actually offers a lower resistance for the flux to flow. Right? So another word that is used is that the material is permeable, that it allows flux to flow through easily. All right. Right. Did I say anything about permeability? Right. So, right. The material is highly permeable to magnetic flux. That is, it allows flux to pass through easily. All right. So the material offers very little resistance to the flow of magnetic flux. And I'll soon remind you of a word for resistance when it comes to magnetic circuit. All right. Now, the source of the flux that you say flowing through this magnetic circuit is actually called a magnetomotive force, and MMF. So the MMF is the source of the flux, similar to how an EMF is the source of the current in an electric circuit. So the MMF is the source of the magnetic flux, and the MMF is due to the current. So you remember the current produces the flux, and the number of turns of the conductor help. So the product of the current and the number of turns gives you the MMF, right? So for a particular current, more turns will give you a stronger MMF, right? So MMF is the source of the magnetic flux. All right. Now, if the magnetic material is made of, is uniformly made, so there are no impurities or no, it's just one piece of material, then and same cross-sectional area, then the MMF per unit length is known as the magnetic field strength. The MMF per unit length is the magnetic field strength. So that's what this relationship is saying. And H is denoted, the magnetic field strength is denoted by the letter H. All right, so the formula for H would be MMF over L, but MMF is equal to IN over L, right? So, and the unit for H then would be amperes per meter. Oh, by the way, some people or some textbook would say the unit for MMF is ampere turns. Ampere turns because you have N turns, but turns is not an SI unit. So the unit is just simply amperes. But you will find some textbooks say ampere turns. All right. So H is the MMF per unit length, and then the unit is amperes per meter. Now, the magnetic field strength for a particular material is related to the flux density by the relationship B is equal to mu naught mu R times H. All right, so H related to the flux density by this relationship. All right, and mu naught times mu R is called the absolute permeability. All right, mu naught is the permeability of free space, and mu naught has this value 4 pi times 10 to the minus 7 Henry per meter. The Hughes goes into some proof as to how they arrive at this. You don't really need to know it, but I know persons like Mr. Duncan and Mr. Atkinson and Mr. Johnson and Mr. Campbell will want to see the proof, so you can always check it out. Mu R is the relative permeability of a particular material. Right? So each material will have a relative permeability. Now for air or vacuum space or non-magnetic material, mu R, the relative permeability is 1. Right? And for magnetic materials though, mu R varies, and it varies with the magnetic field strength for a particular flux density. So you will find that a material will have different relative permeability depending on the value of the magnetic field strength. These curves are called BH curves, and they're drawn for different materials here. This one was taken out of the ebook, the Hughes ebook. But you might notice now that the values are very coarse, so you can really read exactly what they are. So another way of finding them is to give you the data in tables, and you can calculate. So you calculate a value for B, the flux density. You can use a graph or a table with values to work out what the H is that correspond to the B. All right. We will go through. I think we'll go through an example. I think, yeah, to show you how to use this. All right. By the way, if you remember the hysteresis curve, this is actually part of the hysteresis curve. All right. And this is also called the magnetization curve. Now, when you're working on machines, for example, on the power utility at JPSCO, for example, every year or so, they would carry out tests on transformers and the machines to see whether or not, their magnetizing curves are still what they should be, right? Because the curves help you to predict certain operations, right? So if I put in a certain amount of current, I know that the magnetic circuit the magnetic material won't saturate. All right, because up here now you can see it kind of tending towards saturation, and you don't want to operate in a saturated portion. You want to operate more in this linear portion here. So you want to see whether or not, so they would actually raise the current. Remember, H is equal to IN over L. They would raise the current, both positive and negative, and see how the flux density plots out still. Just to make sure that the machines are still operating within their linear portion and there are no changes. All right, so that's something for the future though. All right, the magnetic resistance to the flow of flux in a magnetic circuit is known as reluctance, and it is given by the symbol S. And the unit for it is ampere per Weber. So we can derive different equations for S. Similar to resistance is EMF over current, voltage over current. The MMF, the resistance, the magnetic resistance or reluctance would be the MMF divided by the flux. MMF can be written as IN, and flux is the flux density times the area. MMF can also be written as HL, and then B can be written as mu naught mu RH, and multiply that by the A. Then you'll see that the two H's cancel here. So the reluctance is also given by L, the length of the magnetic circuit, divided by the mu naught mu R, and the cross-sectional area. By the way, the cross-sectional area would be when you cut across here, you would actually see a circular cross-section also. So imagine you cut across it, pull it apart and look at it. Or make two slices and take out the piece that you have cut. When you look at it, you would see a circular cross-section for this type of material.
Sorry, when I get that, go again.
The cross-sectional area. Basically, imagine hold your pen up in front of you, and you cut across it, if you put one end of your pen now facing you, you would actually be seeing the cross-sectional area. All right. So what I'm saying is that if you cut across here, let's say you cut a slice out here, and then you take the slice. When you look at it, you will see a circular cross-section. All right. All right. So there is one more problem. Oh, I think, let me see. Right, one more. So this one actually, I'll actually go through with you, right? And then I will give you a couple of things to do for homework. All right, so this example is saying that a mild steel ring has a mean diameter of 160 millimeters and a cross-sectional area of 300 millimeters square. Calculate A, the MMF to produce a flux of 400 microweber, and B, the corresponding values of the reluctance of the ring and of its relative permeability. All right, so we know the mean diameter, which would be now from the center here to the middle of this, right? And the cross-sectional area, just as I explained earlier, a while ago, would be cutting a slice across here and looking at the cross-section. All right, so so the length of the magnetic circuit.
Sorry, can I go back for 2 seconds, please?
Sorry about that.
And
You
sir,
wanna
I think you had sent this PowerPoint to us now, sir.
You don't think so?
No, sir.
No, I didn't. But you will
So be reminded to send it, please.
You will get it shortly after this. You have seen the others.
Yes, sir. The others have been very helpful. Trust me.
Okay. Well, yesterday, I don't know if you saw, we asked you to read ahead.
Yes,
So
yes, but I didn't have the book. I mean, I'm not seeing it on the classroom. That specific book.
You're not seeing it?
I'm seeing 3 others, but I'm not seeing the birds one. I'm seeing the others, but I'm just not seeing that one that you mentioned.
Which one you see?
And I can see. Let me go back there. But there are several others that I can see.
It's in the WhatsApp group, you know.
Yes, sir. I can see the electrical circuit theory and technology, the Hughes, the will, the
First one is the John Bird, the one that just got the first one.
Which one is John Bird?
Electrical theory.
Oh, that's a John Bird.
Yeah.
Okay, all right, thank you. Bobby Tree never write about John Bird.
Oh, no, I expect that you're going to refer to the books by them author. Because basically all of
realize.
Yeah. All right. The bird is a nice little introduction. Fairly basic, but you can get a quick picture quickly. Yeah, and it gives a lot of practice also. So after the bird, then you can go to the Wildly and to the Hughes. This question came out of the Hughes. So all the books have several questions that you can practice. So Miss Montague, I hope you had read the notes. Yeah. So from now on,
Yes, sir. I had read the notes.
Yeah. Oh, good. Very good. You had read the textbook.
Yes, sir.
Okay. So you found it helpful?
Yes, sir. It was all right.
Okay. Okay. All right. So you were saying that you didn't get this example before.
This example, sir?
Right. You had wanted this example before.
Yes.
No, sir, that's not what I said, sir.
Okay. All right. All right. Yeah. I will try, and as we go along, you will get many of the materials ahead of time. But some of it, I am actually in the process of preparing, so you don't get it. You're not getting it as I'd want to give you ahead of the time. But in time that will come. But what I will do though is to refer you to the readings that can help you in the class, so you'll have a good understanding of the material, even if you don't get the notes beforehand. All right.
Okay, sir, I understand.
Yeah. All right. Yeah, I didn't refer you to the magnetic circuits because since I had asked you late yesterday to just yesterday to read up on electromagnetism, it probably would have been a little too much to read both chapters. But next time I will give you enough time so that you can read both of them, and maybe give you some questions to practice ahead of time too. All right, so all right, let's go through. I can move ahead now.
Yes, sir.
All right, good. So the length of the magnetic circuit equal to the circumference of the ring, right? And that length or circumference is equal to pi d, and the mean diameter was 160. So the mean length is 0.5. I go to a whole heap of decimal places. Just because of some mistake. But remember, accuracy is the name of the game, so try to be as accurate as possible. The flux density, we're given the flux 400 microweber, and we're given the cross-sectional area, so we can work out the flux density. All right, and that works out to be 1.33 Tesla. All right, now what we do now is go to the graph. Now, we know that's 1.33 Tesla. So we look and see where 1.33, which would be somewhere around here, correspond on the mile steel graph. So 1.3 come across here and then come down. I say roughly 2,000, right? If you look in the Hughes though, they actually work with a different figure, but I just have to use the figures what we can see from here. All right, so it's roughly about 2,000 ampere per meter. All right, and then from that now I can work out the MMF. Remember, MMF is equal to H times L. So that would be the 2,000 times the length. So that works out to be just over 1,000 ampere, 1,005 amperes. All right, so that was the first question, was to find the MMF. So we do it like that. We needed to find the flux density, and we needed to find the length of the magnetic circuit. All right, so any question with that? We're okay with that?
So, sir,
Yes.
the question never really asked, tell us what it actually didn't want.
Didn't tell us what way?
The question, sir.
Yeah.
You never really see it ask for the MMF, sir.
Yeah, man. It says the MMF, calculate the MMF to produce a flux of 400 microweber.
Okay, okay.
All right, there's something to point out about the Hughes. Although it's a very good book, they ask the question sometimes in a very weird way, right? So you have to read closely and try to figure out what they are saying sometimes. If I write questions from them normally, like for an exam, I would actually try to put it in a way that make more sense to us. I mean, in the way we speak. So you have to look closely when you're reading. There's also another issue with the Hughes, is that you probably saw it when you were working your problems on three-phase systems, that many of the voltages were the same. Right? But the Hughes, the book that you have is, I think, is the 10th edition. So the book has been around since the 1950s, I think. And many times what they do is just change the voltage in a question, but they don't go around the back and change the answers. So how I found out was because I had an old version that somebody had given me in the 80s when I was a student. So when I compare the questions, I usually see that the voltage values are maybe slightly different. So what was 440 or what 415 became 440 or 400, that kind of thing. So it's not that you calculate, you might find that your answers are off from what's in the book, but many times it's not, because they have changed the voltage value without updating the answer in the book. So
Yes,
bear that
sir.
in.
It happened the other day, you know, and I saw the answer and I said, when you gave us a question and it was in the book. So when I work it out now and then I see the answer. And I couldn't get that answer. So I said, you know what, I keep in my answer now. When I come to class, I have to go explain why that is. Yeah.
They do that, and I think that is kind of poor. But what happened? I think the person who originally wrote the book died, and then you have other persons who have basically carried on the book. I think a person, the last person is Mackenzie, and I think he probably hasn't done too much justice in that regard to the book. So he has changed the value of the voltages, but hasn't updated the answers. All right, so bear that in mind. You will see some of that. And you will actually see it with this question too, because when I work backwards, I realized that they didn't have an 2000 amps as their H. They have 1750 if you work it backwards. So their MMF was about, I think, about 880. But I couldn't use this diagram and then come up with the 880. It's not accurate. And then I check also in the bird. The bird also on page 55 has these graphs too. And the bird actually has their age somewhere over 2,000, maybe 2,200 or so. So all right, I just work with the 2,000 here. So there's a lack of accuracy in the graph. But you will see in the textbook, and next week when we go through some more examples, you will see that tables are also used, and tables can give you some more greater accuracy. All right, to find the values for corresponding to B, and the H values corresponding to B. All right. All right, so let's go. Let's see what part B was. Part B, so we should find the reluctance of the ring and the relative permeability. All right, so let's see if we can find that quickly. So the reluctance is given by the MMF divided by the flux. So it's an easy one. So 1005.2 divided by 400 times 10 to the minus 6. So we get 2.51 times 10 to the 6 ampere per Weber. So you see our reluctance is a large number. And with air, it is even larger, right? And the relative permeability of the material can be found from this. B over mu naught H. B was 1.33. Mu naught is 4 pi times 10 to the minus 7. And H was 2,000. So mu R is 529.19. So it's relative, so there are no units.
So I got 530, so 0.56.
Okay. All right. You probably didn't go to all of the rounding off that or you probably did a little bit more rounding off than me.
No, sir, you round off, sir. I didn't round off.
All right. All right. My apologies, sir. All right. I will send you this now so that you can check these out. There are other questions in the hues, and you can go in the bird also and work these questions on electromagnetism and up to this point with magnetic circuit. Next week we will look at composite magnetic circuit. So you will have magnetic circuit of different dimensions joined together, both in series and I think in series parallel. All right. So,
Sir,
yes.
for exam purposes, given that we're just to say we may come in to do the final. So we get formula sheet circle. What if a formula them have to remember?
Now, let me tell you something. Them gonna become second nature to you now. They will become second nature. You see the amount of practice that you do. You're gonna recite them. If somebody wake up in the middle of the night, you're gonna jump up and say P is equal to root 3 VLIL cos theta.
No, sir. No, sir.
Yeah, some of that easy to remember, sir. But when you jumble up whole heap of them, sir, rough, you know.
No, you're not going to jumble them. You're going to work on a question every night, or a few questions in a particular area. So then it becomes second nature. So tonight you work on three-phase system. Tomorrow night you work on electromagnetism and magnetic circuits.
Sir, I will have a formula, man, sir. We'll do two topics already, sir, and then want a formula already.
Yeah.
Like the whole semester already, sir.
Yeah, but you know, somebody
shouldn't be tested by trying to remember formulas, you know. We are engineers, you know.
So we're not asking to remember them. We're
So
asking
therefore, we should be giving them, give us the problems and the formulas, and we'll find out how to use them.